We start section 8.1 day 2 by doing a quick review of how would you evaluate a logarithm. So the questions in the PDF notes, they kind of show the first step. It doesn't show it color coded. So this is what you'd really be looking at. You would see something like log base 3. Remember, that's a subscript. The 9, I'll call that normal size. And it will simply say, what is this equal? If there was a way to type this into your calculator, and many calculators do have that ability, when you type it in, hit equals, what would it spit out? So here is a technique that won't let you down when you're doing logarithms by hand. Just start off by saying, what does it equal? And I'm going to put an X down. Okay? You're just simply saying, what would this equal? What value? And then what you can do is a rewrite. Okay, so a logarithmic expression or equation can always be turned into its exponential version. And here's how we did it. We did a little loop. We started at the base 3 and we went around in a circle. We went 3 to the power x. 3 to the power x is equal to 9. And then what it becomes is, well, what would x be to make this work? Well, x would be 2. And so then you go back to the start. If you would type in log 39 into a calculator, it would spit out a 2 once you hit equals. Now, that technique will not let us down. For the next guy, when it says, what is log base 2 and then 1 over 16? We're trying to say, what is that equal to? We do the rewrite. So we go 2 to the power x is equal to 1 over 16. Now, this one requires maybe just one more step. A few people could just look at it and say what the power must be. I would do it this way. I would say 16 is 2 to the power of 4. And then you put a negative in front. And let's just evaluate this. This isn't the first time we've seen it. The negative means flip. So this really means the same thing. 1 over 16 means 2 to the power negative 4. And then we have our solution that x equals negative 4. That's what the calculator would spit out if you were typing that in. Once you get used to it, it doesn't matter if it looks really strange. We trust in the technique. Take your expression, that says log base 9, the fifth root of 81, do your rewrite. 9 is equal to the fifth root of 81, 9 to the power x. We're doing the loop around. And then here is what it simply becomes. We just have to get it to the same base, and you guys should have enough experience to be able to do this in just 2 simple steps. First of all, 81 is 9 squared, and we see it starting to appear. The fifth root means the power of 1, 5. So 9 to the power x is equal to 9 to the power 2/5. And now we have our answer. We have our equality just like chapter 7. If we have 9 to the power x equals 9 to the power 2/5, because your 9 is the same, your base, well then x must equal 2/5, and we've evaluated this logarithm. Now, again, just like in the first day of logarithms, I said to you guys, many people can do logarithms until the cows come home and they're like, okay, yep, I understand it. But then if somebody said, well, what really is a logarithm? You might be left wondering, yeah, I don't know what it really is a logarithm. And so in number 2, let's just remember grassroots. What was a logarithm? And this is something that could be a testable question. So we start off with y or f of x equals 4 to the power x. That is an exponential graph. And just give me a moment to get myself set up. This is the line right down the pipe, also known as y equals x. And if I was going to graph y equals 4 to the power x, it follows your basic exponential shape. There is no movement. So there we have it. And we have a horizontal asymptote. And then if we said, what would the inverse look like? What would the inverse to this guy be? Well, an inverse equation, we've taken this as early as chapter 1. We put down the symbol -1. The inverse is the flip over that line down the pipe. This is what the inverse looks like. And then what equation did they give it? Well, it would be a log. Now, because this is a 4, you'd go a base of 4, and then we would put an x down as our normal size. We just wrote the equation for its inverse. And I know it looks strange. Like, why did they have to use log? Why couldn't they have used a different symbol? If you just rack your brain, I can't think of anything else that they could use. So they just said this and it would remind you. Now, what we can also do specifically to the log graph, so I'll keep the color coding in red going. If we said, what is the domain of this red graph? Well, the domain is not all real numbers. It's not greater than or equal to 0. It is just greater than 0. What happens is this y-axis now acts like a vertical asymptote. The original inverse had a horizontal at 0. Well, now we have a vertical at 0. Remember the inverse. We're switching everything. The range is YER. And this is one that you have to commit to memory. It's easy to justify that it goes down forever, but even though it goes like this and it appears to level off, it doesn't. It keeps going up and over, up and over, up and over. It just doesn't go as quickly up and over. This time, you would have no y-intercept, but you do have an x-intercept of a perfect 1 because we haven't done any of the shifts. So again, the y-intercept, we have a none. Now, just to avoid racing, the final part of your day, I'm going to squeeze it in right here. Number 3. We drew a very basic graph for number 3, and it was simply the graph of y is equal to e to the power x. Now don't forget, e is just a number. It's called Euler's number, 2.7, and I can never remember. If we do its inverse, it looks like I'm just repeating myself like old people always do. It's the exact same graph, but here's what is super, super important. This log graph, you'd have the base of e down. And then this is where it gets its own symbol. This e is so important, like basically as important as pi. Well, its inverse is just as important. It's so important they gave it its own symbol. They called it natural log x. And here is what's going to happen. We are learning what logarithms are. And when you look at it graphically, it probably makes a lot of sense. When you look at number 1 in your notes, you're doing it just fine, but you might be wondering where it's going. And a lot of chapter 8, we're going to be doing that. We're going to be just doing calculations with logarithms, learning properties of logarithms, but it's really going to be these two. E and natural log, hand in hand, can do some incredibly powerful things in calculus. So just know that when you want to see what the true power is of a logarithm or an exponential, you do have to wait for a calculus-based course, and then you see where their true potential comes in.